Good morning. Today we will study the theory of L11 parsing. So we started our discussion on top-down recursive descent parsers. Couple of classes back. The main problem with these recursive descent parsers is backtracking. And we would like to eliminate this backtracking. So in this context, we introduce the notion of L11 grammars. And associated parsers, which we call as L11 parsers. So in this LL1, so the first L, it stands for that we scan the input from left to right. This is usually the case. The second L, it stands for that the parser constructs leftmost derivations for the input strings. Construct. And the one here, it stands for one lookahead symbol. In general, when we say LLK grammars or parsers, what it means is that we use K lookahead symbols. In the last class, I mentioned that LL1 is equivalent to LLK, but I would like you to make a note that this is not the case. That is, there are context-free languages which are LLK parsable, but not LL1 parsable. That is, there are context-free languages for which you can construct grammars which are amenable for backtrack-free top-down parsing by using K lookahead symbols, but it is not possible to construct grammars which are amenable for backtrack-free parsing using only one symbol lookahead. So in this class, we will just focus our attention on L11 parsing. So what is the question that we have before us? So we are given an input string W. We are trying to construct a derivation tree for that input string. So we started with the start symbol S, and so far we have made progress till this step. In terms of the parse tree, so this is the start symbol. And this is the non-terminal symbol. And this is the prefix string U. And this is the left of the rest of the string from the intermediate sentential form, alpha. And W is the input string. U is the prefix that is already generated. The current lookahead symbol is A. The question for us is, let's say there are two alternate substitution rules for the non-terminal symbol A, and we would like to use the current lookahead symbol A, that is the terminal symbol A. This is the symbol, the current terminal symbol A, to deterministically choose one of these two substitution rules, alpha 1 or alpha 2 for expansion. That is the question. In order to understand this question, or in order to answer this question, we need to introduce few definitions, couple of definitions. But the idea here is use the current look ahead symbol A to pick A goes to alpha 1 or A goes to alpha 2. The first notation, the first definition that we introduce is what is called as a first function. So for any alpha belonging to NT union T star, first of alpha consists of all terminal symbols such that from alpha we should be able to generate an intermediate form like A beta in 0 or more steps. Let's try to understand this function first alpha using a couple of examples. Let's take this grammar. S goes to 0 S1, 1 S0, epsilon. So here, let's first take first of 0 S1. First of 0 S1 is 0. Because once we start with 0 S1, no matter what we do after that, the initial 0 is going to remain the same. Like for example, we may apply the substitution rule, S goes to 1 S0 and come to a form such as 1 S0, 1. But this leading 0 is not going to change. So first of 0 S1 is 0. Similarly, first of 1 S0 is 1. First of epsilon is also the same. But when you take first of S, while computing the first of S, we need to look at the alternate substitution rules it has, and from that derive what is first of S. So first of S has 0, 1, and epsilon in it. All right. So now let's define one more function called as follow function. So the follow function is defined over non-terminal symbols. Okay, so A is a non-terminal symbol, whereas the first function is defined over string of terminal and non-terminal symbols. The follow function is defined over non-terminal symbols. It consists of all terminal symbols such that from S we should be able to generate an intermediate form like this. Okay, the terminal symbol A follows the non-terminal symbol A in some derivation process starting from the start symbol S. Now let's take the example from the previous example that we have. So 0 S1, 1 S0, epsilon. Note that epsilon cannot be present, epsilon can never be present in the follow function, follow set associated with a non-terminal symbol. So what is follow of S? So follow of S, we can see 1 is present in follow of S, 0 is present in follow of S. That is why 1 is present in follow of S. There is a derivation, one-step derivation from S0, S1, in which the terminal symbol 1 is immediately trailing the non-terminal symbol S. Similarly, there is another derivation in which the terminal symbol 0 is immediately trailing the non-terminal symbol S. Sometimes what we do is, in order to make, like for example, when we are writing theorems, when we are trying to write algorithms, we can take care of the boundary cases easily by introducing an extra substitution rule, or in other words, we say we take the base grammar and we augment the base grammar with a new substitution rule, and we get an augmented grammar. So what do we do? So we take the base grammar and we introduce a new start symbol S prime, and we say S followed by $, where $, is an end of file symbol. And then the rest of the substitution rules remain the same. 0S1, 1S0, epsilon. So in this grammar, in this augmented grammar, follow of S prime, it is null set, okay? So there is no terminal symbol which trails S prime in any of the derivation processes for any input string. But on the contrary, in the augmented grammar, if you look at the follow of S, it has 1, 0, and $, the end of file symbol also. That is, the $, is there in the follow set now because there is a one-step derivation from S prime, the new start symbol, to S$, the intermediate form. So this is what is called as an augmented grammar, where we add a new substitution rule like this to the base grammar. Let's try to understand this by taking a couple of more, one more interesting example so that you get a better intuition. So the grammar that we have right now is S goes to A or B, and A goes to 0A or epsilon, B goes to 1B or epsilon. So what we will do is we will compute the first sets for different substitution rules for different alphas occurring in this grammar. So if you look at first of 1B, first of 1B consists is this. First of epsilon is this. And first of B is 1 followed by epsilon. Similarly, first of 0A first of A is and while computing first of S, we need to know first of A and first of B. It's a union of them. So that gives us first of S as 0, 1, and epsilon. So if we augment this grammar with S prime going to S $, and when we try to compute first of S prime. So you can see, so first of S prime consists of 0, 1 and dollar. So why is it the case? Let's try to understand. So from S prime, you can generate S dollar, and from S you get A dollar, and A you can get 0 A dollar. So using this, we can conclude that 0 is present in first of S prime. We can make a similar argument and say that 1 is also present in first of S prime. But how about dollar? So let's start from S prime. S prime goes to S dollar, and S goes to A dollar. And we can replace A with epsilon, and we'll get dollar. So dollar is also present in first of S prime. We use the ideas from this example to come up with an algorithm to compute the first of various alphas later on in the next class. Now let's try to compute the follow for the different non-terminal symbols in this for this grammar. What is follow of S prime? It is an empty set. And what is follow of S? If you look at follow of S contains dollar. The reason is we have a one-step derivation from S prime to S dollar, and dollar is immediately trailing S. And from this, we can also say that dollar is present in the follow set of A, because we can apply the substitution rule, S goes to A. So follow of A is equal to dollar. We can apply the same substitution rule to compute the follow set for B, which turns out to be the same. Okay, so these are the different follow sets for the different non-terminal symbols that we have for this grammar. So now let's move on. Again, we will revisit the construction or computation of the follow set in a formal way in the next session. So in this session, we would like to understand how we can compute these first and follow sets in an intuitive fashion. Later on, we will come up with an algorithm to compute the first and follow sets. So now let's look at the problem that we are trying to address in the context of L11 parsing. We have the string W is equal to UAV, and in the process of derivation, we made progress thus far. In terms of parse tree, the parse tree looks like this. This is U, this is alpha. The current lookahead symbol is A. The non-terminal symbol that we have to expand is capital A. It has two substitution rules. A goes to alpha 1 and A goes to alpha 2. So the idea here is, let's say, if the current lookahead symbol A, if it belongs to first of alpha I, then what we can do is we can use, if this is the case, use the substitution rule, A goes to alpha I, to expand the parse tree. So here I can be 1 or 2, no problem. But on the contrary, let's say A does not belong to first of alpha I. But what we have here is epsilon belongs to first of alpha. So this is interesting and this is useful because we can possibly use this substitution rule, A goes to alpha I still, to proceed with the parsing process. So we take this A and we expand it using A goes to alpha I. But since epsilon belongs to first of alpha I, that means from alpha I, we can generate epsilon. So this whole tree, this whole parse subtree can be squished to epsilon. So this is all right because the rest of the input string AV might still be generatable using the alpha that is present here. So the possible parsing approach or the derivation process using in the second case is this. You start with S, you have UA alpha, you replace A with alpha I, in 0 or more steps you squish alpha I to epsilon and you get this U alpha. And from alpha we might be able to generate the rest of the input string. So this is a possible parsing approach we can take. This is a possible derivation this is a possible way in which the derivation can unfold. So if you see, for this to happen, so from alpha we should be able to generate A beta. Okay, make a note of it. See, this whole thing implies, this whole derivation process implies that since from alpha we can generate A beta, so it is possible to generate an intermediate form like this. Then this whole thing implies, this whole derivation implies that the terminal symbol A belongs to follow of U. So for us, what this implies is, in order for this derivation process to successfully unfold, the terminal symbol A should be present in the follow set of A. Okay. So these are the two things. So we are seeing two cases. In the first case, we can use the substitution rule A goes to alpha I if A belongs to first of alpha I. In the second case, the terminal symbol A does not belong to first of alpha I, but epsilon belongs to first of alpha I, and A belongs to first follow of A. And because of that, we might still be able to use the substitution rule A goes to alpha I to successfully unfold the derivation process or finish the parse tree construction process. We can summarize this discussion in a different form so that we can arrive at a suitable L11 parsing strategy. So what we have here is the input string W is equal to UAV, and we are considering whether we should use a substitution rule, A goes to alpha I to expand the parse tree. So there are two cases here. The first case is alpha I epsilon belongs to first of alpha I or not. So let's say epsilon does not belong to first of alpha I. Then the only way by which the parsing process can succeed in this case is the current look ahead symbol should belong to first of alpha. On the contrary, if epsilon belongs to first of alpha I, then there are two possibilities. Either the current look ahead symbol A belongs to first of alpha I, or A belongs to follow of U. This idea is nicely captured in the definition of what is called as a first plus function. So first plus of a substitution rule is defined as follows. There are two cases. The case one, the first case corresponds to the no branch here. This is case one. That is, epsilon does not belong to first of alpha. In this case, first place function is simply defined as first of alpha. The second case is epsilon belongs to first of alpha I. This corresponds to the branch S here. In this particular case, first place function is defined as follows. Union follow. And what's the key idea here? If the current look ahead symbol A belongs to first place of a substitution rule, use the corresponding substitution rule. That's all. This is the key idea. However, if there exists two substitution rules, A goes to alpha I and A goes to alpha j, such that first place of A goes to alpha I intersection first place of A goes to alpha j, this is not equal to null. If this is the case, then what happens is during the derivation process, we may encounter a terminal symbol, and when we encounter the terminal symbol which belongs to this intersection set, then we are not sure whether we should be using this substitution rule or this substitution rule, in which case the grammar is not L11 parsing. So this is the summary of the theory of L11 parsing. We'll try to gain more intuition about this L11 parsing by looking at a couple of examples.